Hi everybody, welcome to this tutorial on logic meets learning in infinite domains. I'm Vaishak Belle at the University of Edinburgh. Broadly, what this tutorial is concerned with is the idea of the long-standing challenge and differences between the deduction regime and the induction scheme. So essentially, this is one of the fundamental issues in philosophy, cognition, and artificial intelligence. And deduction typically is concerned with questions about the expressiveness of formal languages. How do you capture information about the world? How do you reason with it using proof systems and whatnot? And so typically we resort to the domain of mathematical logic for deduction, whereas in induction we're typically concerned with how to generalize from examples. So we use probability theory, and statistical machine learning relies on networks of random variables to basically attempt to do learning. Now, historically, these camps have somehow divided the field, but as we know for the past 20 to 30 years, that there have been numerous crossover areas like statistical relational learning, neurosymbolic systems, and high level control. So, automated planning, where you have to control high level control predicates with low level sensory information. And these areas have kind of showed that this kind of dichotomy is not very constructive, and it may even be ill formed, right? So, in some sense, there are complementary aspects to it. Logic encourages structuring the world in terms of objects, properties, and relations. Whereas with probability theory, we end up using, at least in most machine learning systems, independent and identically distributed random variables. So how much does it matter that logic can structure the world? So just to give a very quick kind of example. So if you're trying to encode the rules of chess, for instance, in first order logic, this can be done in a page, whereas it would require 100,000 pages, in propositional logic. Similarly, if you're trying to model, say, a card game, and you say that some person has seen the queen of clubs, and you're trying to wonder what are the remaining cards in the stack, in propositional logic, you would have this large disjunction. Whereas in first order logic, you can simply say there exists an X such that X is not the queen of clubs, and this existential quantifier would be quantified over the set of all cards. And this is sufficient to express this knowledge. But I want to argue that the connection between logic and learning is much deeper and not simply restricted to relational modeling. For instance, there have been long-standing questions about what exactly common sense knowledge looks like, and we kind of understand that it certainly has to involve concepts like time, space, abstraction, causality, and despite methods like deep learning that have been really successful in a whole range of applications, people are now recognizing that, for a number of reasons, once you go beyond standard big data classification tasks, if you want to consider things like model reuse, transferability, again, causal understanding, abstraction, explainability, and efficiency, it does make sense to further augment these models with logic and programmatic structures. Finally, from the perspective of human cognition, we do have this idea that we want to combine deliberative reasoning with low-level sensory information that is purely reactive, and perhaps this logic learning bridge can address some of this. So the purpose of this tutorial again is not to resolve this debate. We won't add further comments, but we really want to provide further evidence for the connections between the two camps and why we need to look at the unification of strategies and ideas between these two camps. So I want to divide this tutorial based on a recent seminar I attended into three possible strategies and themes. Okay, on the one hand, I want to focus on logic versus machine learning, where I am looking at how logic-based techniques can potentially help in addressing some of the challenges, computational challenges we have in machine learning. Then I want to look at machine learning for logic, where we are looking at the learning of logical artifacts like formulas and programs and whatnot. And finally, I want to see how logic can contribute to machine learning. And here I really want to emphasize how logic can help us understand the boundary of tractable and intractable problems, but also using logic as a declarative framework and meta theory to talk about learning. And I will clarify what this means as we progress. One other thing I want to point out specifically regarding the subtitle of this tutorial about it being specifically focused on infinite domains is that there is this common misconception that logic is for discrete things and probability theory in machine learning is for continuous things. Okay, so this is a gross misunderstanding because of course logical formulas are discrete structures, but they can express properties of continuous and even uncountably infinite properties fairly easily. And so in this tutorial specifically, I will try to bring out those aspects to kind of distinguish itself from other tutorials focused on logic and learning. And I will try to show how logic has helped us to understand how learning can be addressed in these more in the continuous and the uncountably infinite cases. Okay. Once again, I'm not going to focus so much on the technical aspects besides giving some basic definitions. So it's just a teaser for the main ideas. I encourage the viewers to see the paper and the references within to get more details. So to start with the first theme, this is a comparison in some sense or a challenge between logic and learning, and basically we want to consider the problem of how logic-based solvers can help in inference and learning tasks. So where does logic really play a role? So consider that the classic problem in learning, which is the problem of structure learning, is you're given some data D, and you're trying to guess some network N. Okay, and what happens is that you run a loop, and in each loop you basically take a guess for what this N might look like, and you want to assess the score and check whether the score of this new guess is better than the previous guess. Roughly, the score of this guess is proportional to the fit of this guess with respect to the data, so the log of the probability of D given N. But at the same time, a trivial guess is simply to reconstruct the data completely. So you don't want to overfit. You also don't want an extremely large model that simply reconstructs the data. So you want to penalize the size of this network, okay, so size of this model. And so you pick a network only if the score of the new guess is greater than the old guess, as I mentioned. Now, the key bottleneck here is this challenge of inference. Now, inference becomes really challenging when you have deterministic constraints, you have a logical or relational syntax. Let's see a few quick examples of what these kinds of syntax mean. So this kind of syntax is very, very natural in most real-world problems. Okay, so for instance, if we are considering the case of, like for instance, any ontology that is being used in a machine learning context. So in this case, for instance, we're looking at the interaction of proteins, and you're trying to build a machine learning model that leverages this ontology. You kind of see that again, you have a relational structure here. Another popular representation in the statistical relational communities is this representation called as Markov logic network. So what this allows you to do is to specify, using a logical syntax, a fairly complex Markov network with relational features. Okay, so for instance here you would say something like, for a randomly chosen person, if this person is friends with another person, the probability that the other person smokes, given if the first person smokes, is 0.9. Similarly, if a randomly chosen person is a smoker, the probability that he also coughs is 0.6. Okay, so you would get a Markov network like the one on the right hand side. But you could also have hard constraints, right? So you can think of these as soft constraints, probabilistic statements, these assertions. But you could have hard constraint that says, for instance, if X is asthmatic and X and Y are family members, then Y is asthmatic too. And you want this constraint to potentially apply to every possible world. So you could either give it a weight of infinity, but nonetheless, this is a hard constraint that applies deterministically. Another representation that's also very popular is probabilistic logic programming. An example here is ProbLog, and here I'm using ProbLog to represent a composite event. So I'm talking about two coins. One is a fair coin and the other is an unfair coin, in the sense that heads can fall with the probability of 0.6. And I have a composite event here which says that I'm looking for two heads in a sequence. Okay, and you can of course then compute the probability of this composite event, and of course this would be the product of 0.5 and 0.6, giving you 0.3. So ProbLog generally fits in with probabilistic programming, something we will come back to, which is a paradigm in machine learning to structure machine learning in terms of modules and have some compositional features. So in that sense, this is another kind of way you could logically structure probability distributions. Finally, here's another example of how hard constraints can play a role in the probability space. So this is the case where I have a bunch of courses. I have probability theory, I have logic, I have knowledge representation in AI, and I have a constraint at the bottom which says that every student takes probability theory or logic, and if they take AI, they must take probability theory, and if they take knowledge representation, they must take either AI or logic. Okay, so I have a constraint of this sort, and as you can see on the right side, this automatically means certain points in your probability space are basically get zero probability, so they should be ignored, right? So of course you can do this with sampling and so on, but it does become extremely hard to control your samples to avoid such problematic points which you want to avoid completely. So one technique that has emerged from the logic literature is this notion of weighted model counting. And just to briefly recap, recall that SAT, or satisfiability, is the challenge of coming up with a model or an assignment to a propositional formula. And sharp SAT extends it further in terms of counting all possible assignments. Weighted model counting is a further extension of SharpSat, which allows you to specify weights on models factorized over literal. So I'll give a formal definition very quickly, but the key idea here is that you might have any of these heterogeneous representations like factor graphs, Markov logic networks, and programs and whatnot, and you reduce this to a weighted model counting formulation. And if you come up with generic schemes to solve weighted model counting, you essentially get the same solver for one of these representations, right? So you have a general purpose solver, and it turns out that this technique does, guarantee state of the art in many benchmark problems. There are many ways of doing weighted model counting. One strategy is called as knowledge compilation, where you build a circuit, which you can see on the right side. But there are also sampling techniques and so on and so forth. Just to quickly talk about the circuit, because it's something that we will come back to. Notice that the circuit is such that it has Boolean variables at the leaves, and they're connected in terms of ands and ors. Recall that an AND gate is one that outputs a positive value only if both the inputs are positive, and an OR gate is one which outputs a positive value if at least one of the inputs is also positive. So the point here would be that you would take a propositional formula and you would construct one of these circuits, and these circuits have different properties, but the most important thing is that once you construct this circuit, which could take exponential time, so while SAT is NP complete, you don't get reasoning for free. Basically the compilation step could be expensive, but once you construct this circuit, it becomes then possible to reason efficiently on this circuit. So basically doing one pass over the circuit can help you answer some kinds of questions we're interested in. At least in the probabilistic setting, we are interested in things like computing conditional probabilities. Okay, so let's just quickly see an example of what all of this looks like. I have here a propositional formula in conjunctive normal form, which says that x or y and y are not z. Okay, so SAT, again, recall, is finding one assignment. So I have found one assignment. You can substitute these values to see that the formula returns a 1. SharpSat would find all assignments, and these are all possible assignments to this formula. Equivalently, because there are 3 variables, there are 8 possible models, 8 possible assignments, and you would say that this has a satisfying probability of 5 by 8. Okay, so that's SAT and SharpSat. Weighted model counting is an extension, as I mentioned. You could also deal with a kind of a finite domain relational language too. So you have some predicate symbols, you have constants, you ground it out. Here is the key thing: you specify a weight function that maps literals of this propositional formula to real numbers. Okay, And so the formulation of weighted model counting is that you look at all possible models of this formula, which is like sharp set. But now you see that you then compute the product of the weights of the literals that are true at this model. Okay. Again, we'll see an example of this, and you can use this to compute, for instance, conditional probabilities as follows, where if you're looking at the probability of Q given E, you would basically look at the conjunction of Q, E, and this formula, and you would divide it by the evidence E and the formula, and look at the weighted model count ratio in this case. Here is kind of a very simple Markov network that does this. On the right side, okay, you have a hard constraint, not P or not Q. And then you have three probabilistic constraints. So one is directly on the literal, the second one is a formula, and the third one is an implication. And this might correspond, loosely to a Markov network like the one at the bottom. So how would you do this? Recall that weighted model counting requires you to put the weights on the literals, which means that you have to introduce new propositions. You would say, for instance, F1 if and only if P or R. So this would basically then capture this disjunctive formula. And of course, then you would specify weights on these things, right? So you would say the weight of P is 0.1, the weight of F1 is 0.8 based on the disjunction, and you do similarly for the implication, okay? And then you assign a weight of 0.6 to that. And if you're looking at a model, for instance, P not Q, R, F1, F2, you can everything else would be assigned a weight of 1. Okay, so as I mentioned, the weights only apply to the literals. So this is a trick to basically handle implications and disjuncts in this formulation. So if you looked at this model, then the weight would be the product of these three things. You can quickly verify that. Okay, so this way you could represent a Markov network and get away with weighted model counting. Okay, so all of this is discrete, right? And of course, that's not surprising. We're using propositional logic, so we are typically dealing with discrete finite outcome distributions only, but we do recognize that, in a large number of applications from planning, robotics, web mining, and vision, you typically want to combine discrete and continuous features. And that's one level of infinity, right? So it's continuous and a notion of infinity. But you can also have countably infinite domains. So typically, for instance, when you write down sentences in first order logic, in most knowledge representation papers, people typically have in mind a countably infinite domain. So for instance, you want to say that the parent of a parent is a grandparent for the entire countably infinite universe. So think of, for instance, natural numbers, right? So for every natural number, assuming each natural number corresponds to a person, this property definitely applies. Now, the literature, at least the conventional literature from the machine learning landscape, tries to address at least the continuous case using variational methods, or in certain cases, for instance, conjugate distributions like Gaussians, you can have certain analytical properties, but to a large degree, these are, provide only weak asymptotic guarantees. So kind of the question here, at least for the continuous cases, and also for the countably infinite cases, can we engineer general purpose methods that deal with logical constraints in infinite domains? Let's consider the continuous case first. A few years ago, some collaborators and I, and since then it has been improved upon in numerous ways, we came up with a formulation called as weighted model integration. Okay, so this was seen as a generalization of weighted model counting. The key difference, if you look at this formulation here, is that again you have a sum of product, but you have this integration symbol there. And what this is doing is that it's taking one of these, what we call as a weighted linear arithmetic formula, and I will tell you what that is in a minute. It's counting all the models, and then it's integrating over the weights, the product of the weights, right? So the product of the weights of the literals in this case will now correspond to a density. And so the density has to be integrated over a certain range. And this would be done for every possible model. Okay, so let's look at an example shortly, but just to kind of give you a quick preview for how this is possible. In the figure at the bottom, you see a Gaussian, so the dark gray line is a Gaussian. And notice that I could take this Gaussian and decompose it in terms of piecewise structures, okay? I could do a piecewise constant, so then it ends up looking like this kind of building, really. But it could be much finer, okay? It could be pieces where each piece is, the density is represented by a polynomial, so it would be more circular. And you can see two possible decompositions on top. So you can see the piecewise constant, where for each of these pieces I give a flat density, I give a number, but I could also give some kind of polynomial equation that captures this. Okay, so essentially I've taken a Gaussian distribution, I've kind of represented this Gaussian distribution in terms of these polynomials, and you can do this to an arbitrary granularity using things like Taylor expansions and whatnot. So this is a fairly expressive mechanism, but of course in the interest of efficiency, you might be satisfied with coarser decompositions of distributions like the Gaussian. So here again is a very simple Markov network for doing this. I have a constraint that, for instance, P is a discrete variable and X is a continuous variable. And I have various weights specified here. So the weight of P is 0.1 and the weight of not P is 2x. So coming up with these weights, of course, is the modeling problem, but in this case, for the sake of illustration, I've kept it at a fairly high level, a fairly abstract level, and I'm not going into the details of how I arrived at these weights specifically. So I have these weights, okay? So if I'm looking at, for instance, the weighted model integration for P or Q, so notice what I'm doing now is that I'm taking this continuous formula with x being between 0 and 10 and abstracting it as a proposition Q. And so why do we do this? This is mainly because the time when we proposed this framework, we were leveraging a property of solvers that could deal with linear arithmetic. These are called as satisfiability modular theory solvers. What they do is that they take one of these continuous formulas, they abstract it as a proposition, they reason at the propositional level, they check that the propositional level is still consistent, and then they return back a model. Okay, so all this to say that it's easy to think of this abstraction, and when it comes to computing the weights of the models, which now becomes a volume because you have to integrate over a density, you kind of reverse it and reintroduce the actual interval. So let's see how this happens. So I've abstracted x between 0 and 10 as this proposition Q. Now the weighted model integral of P or Q becomes the volume of these three different possible propositional models. And for each of these models, now notice what I'm doing is that when I do the integration, I'm reintroducing the interval, right? So x is between 0 and 10. I take the weight, a product of weights of the two literals. So in this case, it happens to be 0.1, and then I integrate and get the volume, okay? And basically, we can show this is correctness preserving in the continuous case, exactly like how weighted model counting is correctness preserving in the discrete case. So this was inference for the continuous case. What about the countably infinite set? So if you're thinking of natural numbers. So again, recall that what we want to do is that we want to state properties that for every individual corresponding to a natural number, the parent of a parent is a grandparent, right? Now, one thing to keep in mind is that in the absence of the finite domain assumption, it so happens that first order logic, as you know, is undecidable. So you do get undecidability. So what can you do? One option is to do some kind of forward reasoning. Okay, so basically, you have countably infinite worlds. So let's say you sample a few of them, you compute the probability. Okay, you compute the probability base for each of these possible worlds, and then you sum them up. Okay, so essentially each sample corresponds to a possible world. Now, the only trouble with this is that there is, of course, countably infinitely many worlds. So essentially, you have to sacrifice an exact inference. That's one approach. The other approach is to basically do some kind of local grounding, as I'm going to call it for this paper. So what you do is that given your query and evidence atoms, you define the estimation for the finite submodel corresponding to the query and evidence. Okay, let's see how this works. So this is a definition for doing weighted model counting in the countably infinite set. And let's kind of see what the issue here is. Recall that again, if you have a very simple formula, like for instance, for all x taken from a domain D, a smoker x, again, if the domain is just of size 2, you have 2 atoms. So of course, if the size of this domain is a set of natural numbers, you have countably infinite domains, okay? Now, one result we have here is to kind of define a version of open universe grounding. And what it does is that it grounds the formula with respect to the constants mentioned in the formula, plus a few arbitrarily chosen ones. Okay, these arbitrarily chosen ones can be thought of as kind of placeholders, really, or even abstract constants that apply to the whole range of constants not mentioned. So let's see an example. Again, if we take the smoker example and the domain is, let's say, AB, or let's say the constants mentioned in the formula might be, there might be 2 instances of smoker for A and B. We need 1 extra constant because we're looking at the number of variables mentioned in the formula. Now the theorem goes as follows. It says that given a first order clausal formula, one of these quantified formulas as delta, given a ground formula alpha, if you want to look at the entailment of delta, of alpha being entailed by delta, it suffices to look simply at the open universe grounding of delta and not alpha. So typically recall that if you want to look at entailment, this is entailment of refutation. But again, you're looking only at this very small grounding. Let's look at an example, okay? So let's say the delta in question says the following, that if X is a smoker and X and Y are friends, then Y is a smoker too. Let's say that John is a smoker, and let's say that everybody is friends with John, okay? And the query in question here, alpha, is that is Jane a smoker? Now, you could kind of see why this is true, right? Because if everybody is friends with John, then it certainly is the case that because John is a smoker and that Jane is John's friend, she must be a smoker too. No, but notice that the constants mentioned in this knowledge base alone are not sufficient to answer this query. So in principle, you would need to consider an infinite grounding, but what we're able to show again is this kind of local grounding, where it suffices to look at just the constants mentioned and 1 extra one, and it turns out that you can apply the theorem from before to prove that this is indeed entailed. Now I have ignored weights in this example for simplicity, but you can also do this with weights. Okay, so this is a version where you can kind of not necessarily ground for all the constants in a domain, but look at only a finite subset. So that's the idea here. Okay, so I've looked at now the problem of how logic-based solvers can contribute to reasoning in the infinite in the both continuous and countably infinite setting in the context of logic versus machine learning theme. Let's now move on to the next theme where we use machine learning for logic. So really what we want to look at is how the machine learning can contribute for learning logical artifacts. Now, again, keep in mind that from a historical context, inductive reasoning has been kind of a core concern in the logical worldview because we really need some kind of machinery to obtain knowledge, right? So we cannot expect the entire knowledge base to be completely specified for the human by the human. So we need some kind of plan. And again, learning of these logical and symbolic artifacts has been an important issue in AI. It comes up in plan synthesis, it comes up in program induction, and a whole range of other areas, automated learning, etc. And we're considering again, the fact that there has been a lot of work in the propositional and finite automata settings. Okay. I don't want to be too broad about this, but at least in my view, there might be two simple ways to think about the broad strategies that have emerged, at least in the AI literature, regarding how you can learn logical artifacts. One is follows the so-called inductive logic programming regime. So basically, you're given some logical language L, you're given some background knowledge B, given some examples D, and you want to find a hypothesis such that the background knowledge along with the hypothesis entails the examples. Okay, that's one way of doing this. So this is entailment-based scoring, if you will. Another approach is goes back to one of the first slides I had, where you pick a hypothesis such that the score is greater than the previous guess, and again the score is proportional to the fit of the data for the hypothesis while penalizing the size of this hypothesis. Now, these are just at the very high level the two possible ways of inducing this hypothesis, but there are many variants possible. There's Bayesian scoring, there's neural synthesis, there is also an approach referred to as the pack semantics, where you try to guess a hypothesis that is provably correct with respect to an unknown ground truth. So that requires some other kinds of definitions and mechanisms for that. So there are many variants here. Let me very quickly talk about some work and some results we have regarding the infinite case. One thing we can do is try to figure out whether we can induce programs that mention continuous properties. Okay, so recall that we discussed ProbLog as one of the discrete options for modeling probability distributions. Now the question is, can you learn a continuous variant of it, where you have continuous features in the program? And here is a way of doing this. So imagine you have a whole bunch of points, okay? So this is a bit like learning a weighted model integration, right? Or at least contributing to the learning of weighted model integration, where what you're trying to do is induce weighted atoms. So you want to learn weighted linear arithmetic formulas. And here's an approach where what you kind of do is that, given a bunch of data points standing for real valued instances, you categorize them or you intervalize them to certain intervals, and then you learn a polynomial that best fits these intervals. Okay. What this kind of ends up looking like is a program of this sort, where for instance, you have discrete variables. For instance, you have luck, which is there's a 0.8 probability of luck being true, but you also have intelligence, which turns out to be a continuous, which is of course a continuous property, as being characterized by this kind of weighted interval formula, which says that if the intelligence is between 114 and 124, these are IQ points, then this would be considered high intelligence. And this kind of piece in this continuous distribution is given by the polynomial. Okay, so you basically end up learning something like weighted model integration, but in the context of ProbLog. Similarly, recall again that we discussed circuits when we talked about knowledge compilation, and there is an area of machine learning that is specifically focused in terms of learning these such circuits directly from data, and they correspond to essentially learning a kind of joint distribution over the variables. And again, the learning paradigm here is that you're trying to do some kind of likelihood fit. So you're trying to see, well, you're trying to optimize to make sure that the data is a good fit for the given model. And this is, of course, in the discrete case because you have Boolean variables. But again, leveraging the weighted model integration and weighted linear arithmetic learning, you can construct a kind of continuous version of this. And here you would be able to, for instance, ask questions like, what is the probability that somebody is male, given that their height is greater than 180 centimeters and the weight is greater than 200 pounds, right? So the conditioning here is a continuous thing, whereas the query itself is a discrete thing. So you can have combinations of discrete and continuous, and the idea is to plug in this kind of weighted model integration learning in the context of these discrete circuits. I want to very quickly mention that this is not all the literature is doing. There's a lot of other ideas out there. I'm just going to discuss a few examples where people have gone beyond the intervalization. One recent work by David and Nitti has kind of focused on this approach where you're trying to learn this discrete continuous, again, a ProbLog program called as a distributional clause. And this clause, for instance, is kind of saying that if I do a move action, then the position at time t plus 1 is the position at time t plus some Gaussian noise, okay? They do this by a kind of a decision tree learning where they restrict themselves to Gaussian distributions for the continuous part, but nonetheless they do provide this kind of hybrid program as one being induced. You also might be interested in not learning just intervals. You might be interested in learning oblique constraints, so things like, for instance, x is greater than y. So this is really somewhat similar to a linear program, and you want to learn these from data. So there's been some work by Samuel Kolb at KU Leuven who's been doing that. We have also done some other work where we are trying to learn such constraints as well, but implicitly. What that means, I will give an example of this, of another instance of this framework shortly. But really the key idea is, if you have a knowledge base which has sentences like x plus y is greater than z, x is greater than 5, and you have a whole bunch of noisy measurements like z might be 0.1, z might be 0.9, does it follow that y is greater than z, right? So you want to ask these kinds of questions, and we provide a framework for doing that with some correctness guarantees on what is learned. So these are cases again where we have gone beyond the discrete to the continuous setting. Okay. What about the countably infinite setting? So this gets very interesting, but also tricky. Okay. Notice the key difference here. In the continuous setting, what we were trying to do is, given a bunch of real valued examples, we were trying to kind of draw or learn an interval, right? Which is fine. But in the countably infinite setting, you want to somehow learn these kinds of clauses which says that for all of the constants in my domain, which might be countably infinite, the parent of a parent is a grandparent, right? Now this is tricky because of the following reasons. In the case of the continuous, you are somehow approximating the way the data was distributed using these intervals. But in this case, you want to look at some examples and induce one of these clauses, and the question is, what really justifies this, right? What allows us to do this? Now it turns out we can leverage one of the results we talked about. So we talked about this open universe inference scheme where if we were looking at the entailment of a causal first order theory delta and the ground formula alpha, it sufficed to look at this open universe grounding, as we call it, which is a finite grounding. And it turns out that we can leverage this theorem to now do learning, okay? So the key idea here is that you have background knowledge which possibly contains universally quantified formulas, and you observe examples, and again these examples are ground instances. They may even be noisy examples. Based on these examples, you want to induce first order clauses to answer a query, okay? And again, this becomes possible because we leverage this finite grounding, finite submodel property to induce with the provable guarantees that we're doing the right kind of induction of the clause. Let's look at an example to see what this is. The one thing I will say that learning this hypothesis explicitly, as far as we know, is intractable. So we propose what is called as an implicit learning scheme, and maybe this is again best illustrated using the example. Let's consider this background knowledge where I have statements like everybody other than Logan is a mutant, and that if X is a mutant and X and Y are team members, then Y is a mutant too. Okay, so this is my background knowledge. I observe now that Scott is a teammate with Logan, and I observe now that Jean is a teammate of Logan. And my query here is Logan a mutant too? Okay. And it turns out this query is indeed entailed. Why is that? It turns out that by looking at these two examples, you can induce the following universally quantified formula, which says that everybody other than Logan is a teammate of Logan. And this is actually a powerful conclusion, right? You have only seen two examples of people being teammates with Logan. And just from these two examples, you have concluded, right, with very high probability that everybody other than Logan is also a team member of Logan. Okay, so this is where this kind of finite submodel property gets used, because we recognize that in some sense, seeing these two examples, they are placeholders for all the ones not mentioned, which allows us to conclude or induce this kind of universally quantified formula, and therefore we get the queries entailed. So in some sense, what you really get is the background knowledge plus this implicit theory allows you to entail the query. So this is a bit like inductive logic programming, in the sense that you're trying to induce a hypothesis in service of answering a query, but except that the hypothesis is left implicit for tractability reasons. And we have these correctness guarantees that this induced hypothesis is correct with respect to the unknown ground truth. Okay, it's probably useful if you're interested to look at the paper to kind of see how this works. That concludes the second theme. Let me now turn to the third theme here, which is logic for machine learning. And again, here now we're using logic in service of machine learning. We use it for correctness, data efficiency, compositionality, and many other problems. Okay, let's see what these are. Very quickly, there are many dimensions to how logic can contribute to machine learning. One very popular approach in many machine learning conferences right now is to kind of use symbolic domain knowledge to make learning better, more efficient, more effective, more reliable. So you look at work on relational embeddings, you look at loss calibration, where you try to train a deep network with respect to symbolic constraints, with the hope that future predictions respect this constraint. So there's been a lot of work on that. Citations can be found in the paper of this tutorial. There's also a whole range of hybrid knowledge representation approaches that combine declared knowledge and learned predicates. Again, you're kind of learning the low-level stuff, and then you're using a high-level KR theory to kind of coordinate and reason about this low-level predicate. So in this sense, you're empowering the learned structures with some kind of high-level knowledge. So there's been work on that. There's also recently there's been a lot of work to show that logical circuits are fairly competitive to standard machine learning approaches. So there's been logical alternatives really to standard machine learning. There's also a lot of work on trying to verify the properties of learned models using temporal logic specifications and other kinds of mechanisms, model checking. What I want to here quickly preview is probabilistic programming as one way of providing, some kind of meta theory to machine learning, and an approach called a direction of work called as abstraction, which also provides some kind of meta theory to machine learning. Let's see what this is. Now, let me point out that the distinction between the finite and the infinite is not so urgent in this case. You could imagine first order constraints, for instance, being used in a learning context, but there is not much to be said regarding this distinction in the content that follows. Okay. Recall what probabilistic programming was. I talked about ProbLog as an example of probabilistic logic programming, which is a way of structuring probability distributions. So for instance, the left one is a program you've already seen, where I defined a composite event based on two heads falling. The right one allows us to define a mixture distribution. Okay, so it says that a heads again is an unfair coin with a 0.7 probability of falling heads. I have two random variables A and B, and I define tails as the opposite of heads, and I basically say if I consider a world where heads has fallen, then I consider a mixture distribution with heads and A. If I consider a world where tails has fallen, then I consider a mixture distribution with tails and B. Okay, so you can define programs of this sort. Surprisingly, and not surprisingly, it turns out that you can reduce such programs, as I mentioned, to weighted model counting. So in this sense, you are able to structure machine learning using logic and then do the computation with this with this kind of enhanced language, again in logic, right? So there's a closed loop here. But there are other ways of solving probabilistic programming, including sampling. But nonetheless, I think probabilistic programming does serve as an interesting symbolic slash logical slash programmatic syntax for structuring machine learning problems, and it's gaining a lot of popularity right now. On that note, one kind of direction that's sort of also interesting is, to a large extent, much of the machine learning, might be focused on the probabilistic aspects, but there are all sorts of aspects of machine learning and artificial intelligence that don't just involve probabilistic computations. Things like SAT is an example, but also you might want to do things like linear programming in certain instances. You might want to plan. And so there is this direction of work at extending or looking at a more general form of weighted model counting, referred to as algebraic model counting, where rather than the sums of products of the weights of literals, you allow these sums and products to come from any commutative semi-ring. So you might look at maximization, max of min, max of product, min of product, etc., etc. Okay. So this is work that's been around, where again you take the discrete case and you kind of allow this generalization for these commutative semirings. But we've also shown that this can be extended to deal with all sorts of non-standard problems, as well as a continuous case, and deal with a kind of composition. So there's a proposal we have called a semi-ring programming, which basically combines a logical syntax with these commutative semirings, with the potential of coming up with a general purpose solver. So what are the kinds of problems we can cover with such an approach? So in the interest of time, I won't discuss in too much detail what these different programs are, but basically by using these commutative semirings, you can capture things like graph coloring, but also counting the number of graph coloring instances, computing matrix factorizations, logical integer programming, and a whole bunch of other problems that you can capture in the same framework, right? So you're thinking of building a machine learning and or more generally an artificial intelligence system where all of these different components and all of these different computations are needed, and you could combine them in a modular fashion quite elegantly. And that's kind of the proposal we had. We also kind of drew a comparison chart to show that this kind of approach generalizes a whole range of other proposals in the literature, including things like constraint programming, as well as semi-ring constraint programming. So a whole bunch of other approaches can be subsumed by this more general form of weighted model counting. And the key point here, I think, again, is that logic is providing the necessary framework and the syntax as well as the structure to kind of do such modeling. And so in that sense, it is going beyond standard big data classification to provide this kind of compositional and rich approach to modeling problems. One thing I want to mention very quickly before I turn to conclusions is that we have also looked at how logic can be used for abstraction. So abstraction is this idea that's very popular in science and social sciences, where you kind of want to take a very complex problem but define it and introduce it and study it at a different level of granularity by omitting irrelevant details. Okay, so in the AI context, you might say, how can I come up with abstract high-level concepts that kind of reason about the low-level feature learning bits? Okay, you might also want to be interested in structuring knowledge hierarchically. Even if you deal with tractable models, right, it's much more effective to deal in a smaller space than a larger space. So the abstraction kind of question that's really driving what I'm discussing here is to study under what conditions can you define an abstraction. What does it mean to have a faithful alignment between two probabilistic models? Let's look at a very quick example to see what this is. Here is a Markov network where I'm trying to define some kind of course grading system, where I have a difficulty of a course from easy, medium, and hard. I have students with IQs from low, average, and exceptional, and I have grades, which is a continuous variable, from 0 and 10. Okay, there are all sorts of abstractions I can do. I can abstract this 3-value difficulty variable into just 2 values, and easy and not easy. I can make G, which is the grade, a discrete variable. I can also come up with a very, very compact qualitative abstraction, which simply looks at whether the probability that a low IQ student fails an easy course is non-zero, and if it is, it alerts the admin. So these are all kinds of abstractions you might want to consider, and we study under what conditions such abstractions can be defined, how can these abstractions be synthesized, what kind of properties would they be expected to obey. I have a slide on this, but in the interest of time, I will skip it. You can have a look at the reference to kind of see what exactly we can do with these abstractions. Now this allows me to sum up. As I mentioned, this work was really trying to study about all the deep connections between logic and learning, and there are many, many connections, many strands. I basically categorize them in terms of 3 broad themes. One, I suggested that logic-based solvers could provide alternate computational schemes. On the second, I kind of discussed how the representation and expressiveness of logic can help us reason about continuous as well as countably infinite domains in a different way. I also wanted to make the point that in some sense logic is allowing us to contextualize machine learning models in terms of verifying, adding domain knowledge, enabling modularity, abstraction, meta theory, etc. So these are 3 concrete ways in which logic can contribute to the machine learning landscape. But there's also the flip side of it. This, in the sense that we cannot expect all of symbolic knowledge to come from humans. We want to learn this from data, and this is where machine learning can also help us. So in this sense, there's lots to be learned and lots to be gained by looking at the intersection of logic and learning. Thank you very much for listening.